In today's video, we will learn about rotational kinetic energy and angular momentum. So when does an object have rotational kinetic energy? An object rotating about some axis with an angular speed is said to have rotational kinetic energy. And we see that rotational kinetic energy is equal to 1/2 the moment of its inertia multiplied by its angular speed squared. And if the object is rolling, then we see that the object has both translational and rotational kinetic energy at that moment. And just like translational kinetic energy, rotational kinetic energy is conserved. As well with rotational kinetic energy, we have angular momentum. And we define angular momentum as being equal to our moment of inertia multiplied by our angular speed. And if we take our change in our angular momentum divided by a change in time, we can calculate the torque exerted on that object. If we have an initial angular momentum and a final angular momentum that are the same in a system at two different times, and we suppose there's no net external torque exerted on the object, then we can assume angular momentum is conserved. If we were to look at our first example, we see that a solid uniform disk that has a radius of 0.25 meters and a mass of 55 kilograms rolls down a ramp that has a length of 4.5 meters and makes an angle of 15 degrees with the horizontal. And the disk starts from rest at the top of the ramp. We're asked to find the speed of the disk's center of mass when it reaches the bottom of the ramp and the angular speed of the disk at the bottom of the ramp. So if we were first to start by summarizing the information we're given, since the disk starts at the top of the ramp at rest, our initial velocity will be equal to 0 meters per second. Our final velocity is unknown, and the radius of the uniform disk is given to us as being 0.250 meters. By looking at our problem and our figure to the right, you can see that our object will have potential energy, rotational energy, and translational kinetic energy at some moment in time down its path down the ramp. So we can use our equation for the conservation of mechanical energy, which states that our initial rotational kinetic energy plus our initial translational kinetic energy plus our initial potential energy is equal to our final rotational kinetic energy plus our final translational kinetic energy plus our final potential energy. If we look at our values, we see that our object is at rest initially. So initially, our object will not have rotational energy, nor will it have translational energy. And at the bottom of the ramp, the energy that had stored potentially will be transformed into rotational kinetic energy plus translational kinetic energy. However, our disk will not have energy in the form of potential energy. So if we were to expand our equation above, see that potential energy is expressed as mass times gravity times our change in our height is equal to our rotational kinetic energy, which can be expressed as 1/2 times our moment of inertia multiplied by our angular speed squared plus our translational kinetic energy is equal to 1/2 times our mass times our final velocity squared. And we know that the inertia for a solid uniform disk can be written out. And if we simplify our equation more, we see that we have mass times gravity times our change in height will be the angle of our incline multiplied by our opposite over hypotenuse, which will give us sine. So we'll have sine multiplied by theta is equal to 1/2 our inertia. And our moment of inertia for a uniform disk is 1/2 times its mass multiplied by its radius squared multiplied by its angular speed. However, since we're trying to solve for our final velocity, we can write angular speed as velocity over its radius squared plus 1/2 the mass multiplied by the final velocity squared. And if we were to get our final velocity by itself, since that's what we're trying to solve for, we see that final velocity would be equal to the square root of 4 times gravity multiplied by the length of the incline times sine of theta divided by 3. Now if we plug in our values for our equation, see that 4 times the acceleration due to gravity times the length of a ramp, which is 4.5 meters, multiplied by the sine of the incline, which is 15 degrees, divided by 3, we see that our final velocity will be equivalent to 3.90 meters per second. And in part B, we're asked to solve for the angular speed of the disk at the bottom of the ramp. And we know that angular speed is the same as our velocity over our radius. And since we know what our final velocity is, we can plug in our final velocity for v, which is 3.90 meters per second, divided by our radius of 0.25 meters, will give us an angular speed that is equal to 15.6 radians per second. In our second example, it states that a bicycle brakes are being checked at a repair shop. The brakes deliver 8 newtons of a friction force to the 1 meter diameter wheel rim. If the wheel is rotating at 10 radians per second and its moment of inertia is 2 kilograms multiplied by meters squared, how long does it take for the wheel to come to rest? So yet again, the facts that are known. We know that the force due to friction is equal to 8 newtons, and that the diameter of the wheel is 1 meter, so therefore the radius of the wheel must be 0.5 meters, and that the wheel has an initial angular speed of 10 radians per second and a moment of inertia of 2.0 kilograms times meters squared. And we're asked to solve for the amount of time it takes for the wheel to come to rest. So we learned that angular momentum, by using angular momentum, we know that torque is equal to our change in angular momentum divided by our change in time. And that torque is the same as having a force multiplied by radius. And if we're trying to solve for time, we can rearrange our equation where we get our change in time is equal to our change in our angular momentum divided by our force multiplied by our radius. And since angular momentum is equivalent to our moment of inertia times our angular speed, we know we can expand our change in our angular momentum to be our final moment of inertia times our final angular speed minus our initial moment of inertia multiplied by our initial angular speed all over our force due to friction times our radius of the wheel. And since our wheel comes to rest, our final angular speed will be 0, therefore making our final angular momentum equal to 0 minus our initial angular momentum minus a moment of inertia, which is 2.0, multiplied by our initial angular speed of 10 radians per second, all over our friction force of 8 newtons, multiplied by a radius of 0.5 meters. So when we calculate this out, we see that the amount of time it takes for the wheel to come to a complete rest is equal to 5 seconds.